In this video, we will review intermolecular forces of attraction, which I will abbreviate IMF, and discuss how they relate to the physical properties of organic compounds. We'll start with our learning goals. To identify the predominant, most important intermolecular force of attraction for a given functional group or for a given molecule. To identify hydrogen bond donors and acceptors. To explain the physical properties such as the melting point, boiling point, and solubility of a given molecule or molecular ion based on the intermolecular forces. And finally, to identify protic and aprotic solvents. Let's get started. Take a moment to predict which of these compounds will have a higher melting point, and then explain your reasoning. Please write down your answer. Last chance. Here's some data. So now that we have this data, look at it, think about it. How can we explain the differences in melting point and solubility between these two molecules? Again, write down your answer. You may have recalled from general chemistry that the solubility of a compound in water depends on its polarity. So you might say that these two molecules have different polarity. We can see that estradiol has two polar alcohol functional groups, while cholesterol only has one. Cholesterol also has a much larger, greasy, in other words, nonpolar hydrocarbon region. Estradiol also has a hydrocarbon region in the middle, but certainly cholesterol's hydrocarbon region is much bigger. Thus, it does seem reasonable that these two molecules have different polarities and that estradiol is more polar than cholesterol, making it more water soluble. Neither of them, though, are very water soluble at all, though, right? Only 3.6 milligrams per liter. How can we explain the differences in the melting point? We can see that estradiol has a significantly higher melting point than cholesterol. Why is that? Well, the answer also lies in the polarity difference between these two molecules. We know that polarity determines all types of physical properties. We may recall that from general chemistry, such as solubility, melting point, and boiling point. But why is polarity related to these physical properties? What is the microscopic basis for this phenomena? Yes, molecular polarity determines the intermolecular forces of attraction between the molecules of a substance, and those in turn affect physical properties such as solubility, melting point, and boiling point. I have just drawn a diagram of an intermolecular force of attraction. Those two molecules are experiencing electrostatic attractions to one another, and those attractions affect the physical properties of that mystery molecule, so whatever those spheres are. So estradiol and cholesterol, they have different polarities, and so they will have different intermolecular forces. And so those different intermolecular forces result in different properties such as solubility and melting point. And by the end of this lesson, hopefully we can give a little more sophisticated of an explanation for the data that we observed on this slide. However, we have a good starting place. Much of what I've just said probably sounds somewhat familiar to you. Let's take a moment now and activate that prior knowledge that we have. Write down your answers to these two questions. List the different types of intermolecular forces of attraction, and then consider how do you know whether or not each type of intermolecular force of attraction that you wrote down here is significant for a given molecule. All right, last chance. It's likely that you remembered 3 types of intermolecular forces. Maybe another one or two. So dipole-dipole, hydrogen bonding, and dispersion forces. There are many different names for dispersion forces. You may hear them called London dispersion forces, or you may hear them called van der Waal forces, or induced dipole. All the same thing. All right, now how do you know whether or not each of these types is operating for a given molecule? Well, keep what you wrote down handy and check and see if you're right. Let's tackle these one at a time. So dipole-dipole interactions are most significant for polar molecules. We'll take a moment and ignore the specific molecule on the right side of this slide and just think about a generic polar molecule. Polar molecules have an overall molecular dipole, and the opposite ends, oppositely charged electrostatic ends of two molecules will attract one another. Here is an intermolecular force of attraction between those two fictional polar molecules. And of course, this says attractions have a negative energy, so it's good, right? Low energy, good. The example of the dipole-dipole forces on the right side of the screen is between two molecules of dimethyl ether. And you can see that this teeny tiny partially negative region attracts this a little bit larger partially positive region. So it actually turns out that dimethyl ether is not very polar, and that's typical of ethers. It's a little bit polar, but it's not very polar. Polarity is measured. This can be measured in lab. For example, we know that dimethyl ether is not very polar because it doesn't mix with water. And because it's not a very polar molecule, it has pretty weak intermolecular forces of attraction. But for more polar molecules, they can be strong dipole-dipole interactions. So the strength of the attraction will vary from molecule to molecule. And that's based on how polar, how large the regions of electrostatic charge are on a given molecule. For example, formaldehyde is much more polar than dimethyl ether, and it will mix with water. And that's because this partially negative oxygen, it's really sticking out on its own. And then you have this partially positive region down here. So it's much more polar than dimethyl ether, and it will mix with water. So key points here. Dipole-dipole interactions are the most significant for polar molecules. However, the strength of dipole-dipole attractions will vary based on how polar a molecule is. Dimethyl ether isn't really all that polar, and so it has pretty weak dipole-dipole attractions. It doesn't even mix with water. However, a more polar molecule like formaldehyde, it has larger regions or more accessible regions of partial charges, and it makes stronger dipole-dipole attractions. So this intermolecular force of attraction will be stronger for formaldehyde. And so formaldehyde does dissolve in water. Let's look at a special type of dipole-dipole interaction, even stronger than the one that I mentioned between molecules of formaldehyde, and that is the hydrogen bond. A hydrogen bonding interaction is simply a special type of dipole-dipole force. And by special, it just means that it's particularly strong. Hydrogen bonding interactions require very polar XH bonds, where X equals fluorine, oxygen, or nitrogen. Chemistry is fun. Hydrogen bonding interactions also require a hydrogen bond donor and acceptor. The hydrogen bond donor is just that polar XH bond, where since X is quite electronegative, there's a significant dipole. Hydrogen is so small that there's a nice dense region of partial positive charge here. So there's a big attraction to the hydrogen bond acceptor, which needs to be a lone pair, this electron-rich region in our example molecule here. All right, so we have our fictional hydrogen bond donor and acceptor. Here we have two different molecules doing the donating and accepting of the hydrogen bond. And then we have on the right an example of hydrogen bond intermolecular forces of attraction. Again, the intermolecular force of attraction is the electrostatic attraction between the partial positive on one side of the molecule and the partial negative on the other end. So it's just this attraction between those two ends of those two different molecules. I've always hated the name hydrogen bond because I think we can get confused and say, oh, there's the hydrogen bond. No, 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 no. We're talking about the attraction between two different molecules of the substance. So those strong attractions between two molecules undergoing hydrogen bonding intermolecular forces is what makes this a special type of dipole-dipole. It's just particularly strong. In fact, hydrogen bonding interactions are the strongest when multiple hydrogen bond donors and acceptors exist in the same molecule. We could look at example 1 here. Ethanol versus methanoic acid. Ethanol has one site with which it makes hydrogen bonding interactions. However, formic acid, molecule B, has two sites. Both of these oxygen atoms can act as hydrogen bond acceptors, rather than just the one site in ethanol. Thus, there are stronger hydrogen bonding interactions between molecules of formic acid than between molecules of ethanol. This will have consequences on the physical properties of these two molecules. Formic acid we expect it to have higher melting points and boiling points than ethanol, for example. Second, the more polar the XH bond is, the one donating the hydrogen bond, the more polar that molecule. We could compare and contrast an NH bond as a hydrogen bond donor versus the OH bond as a hydrogen bond donor in ethanol. And we would see that because OH is a more polar bond than NH, the partial charges on oxygen and hydrogen is bigger for the OH bond for ethanol, and so we're going to have a stronger intermolecular force of attraction between molecules of ethanol versus molecules of ethylamine. This is reflected in the much higher boiling point of ethanol. Let's move on. We'll look at the third type of intermolecular force of attraction, and one that you have likely encountered before, and that is the London dispersion force. Oftentimes, I abbreviate these as LDF, London dispersion force, but again, they are also known as van der Waals forces, or simply induced dipole or dispersion. Induced dipole interactions are most significant for nonpolar molecules. Now, they exist for all molecules, but they're the weakest type of intermolecular forces of attraction, and so they're most significant when they're the only type that exists for a molecule, as is the case for nonpolar molecules. We'll look at propane as an example of a molecule for which dispersion forces are the predominant intermolecular force of attraction. Propane, being made of just carbon and hydrogen, is a nonpolar molecule. All the bonds are nonpolar. However, electrons are constantly in motion. So although on average, molecules of propane have evenly distributed electron clouds like these two shown on the left, at any given instant, electrons may be more on one side of the molecule than the other because electrons are constantly in motion. And now temporarily, for one moment, there is a dipole for this molecule, just for a moment. And this again is due to the regular and constant movement of electrons. This temporary dipole then induces a temporary dipole in its neighbor so that the electron cloud then becomes polarized in the neighboring molecule as well. And then there is an attraction between those two oppositely charged electrostatic regions, and there's our intermolecular force of attraction. And it lasts for a moment, and then it goes away, and the two molecules go back to being nonpolar with evenly distributed electron clouds. And because of the temporary nature of this intermolecular force of attraction, this is usually the weakest type. It can be quite strong, when molecules have large electron clouds and many regions where these induced dipoles could happen, but usually this is the weakest type of intermolecular force because it's temporary. Let's take a moment and take stock of where we are. So I have a chart here relating physical properties of some selected compounds to intermolecular forces of attraction. So go ahead and take a look at this. You can pause if you want. The discussion questions are, what physical properties are related to intermolecular forces? And then why are these molecules here? Why were they chosen to have similar molar masses? So I'll zoom back in. We can see that these molecules have similar molar masses. We can see they are arranged from the highest boiling point, melting point, solubility in water to the lowest boiling points, melting points, and solubility in water. We can see some of these intermolecular forces of attraction look familiar. So this is hydrogen bonding, where these two molecules exhibit hydrogen bonding intermolecular forces of attraction. We did say that because formic acid, aka methanoic acid, has two sites with which to make hydrogen bonds rather than just the one in ethanol, formic acid does have stronger hydrogen bonding interactions, and that's interesting that it has higher melting points and boiling points and an infinite solubility in water. This means they mix in all proportions. All right, we have two molecules here that have dipole-dipole intermolecular forces of attraction. I showed you formaldehyde, which is related or one carbon fewer than ethanol, this molecule here. But definitely we discussed that the aldehyde would have stronger dipole-dipole attractions because of a bigger dipole here than dimethyl ether, which has a much smaller dipole and weaker in attractions between two molecules of this substance as a result. And then finally, we can see that the molecules with the lowest melting points and boiling points, these all have London dispersion forces or induced dipole forces. So which physical properties are related to intermolecular forces? Well, in this table, there's boiling point, there's melting point, and solubility. So the ability of two substances to mix. And I did mention that polarity, dipole moment, can be measured. So that's what this information is. And I won't talk much more about it. And finally, why are molecules of similar molar mass examined in this table? Well, molar mass or electron cloud size will certainly affect the magnitude of these intermolecular forces of attraction. This table does a really nice job of allowing us to see how the different types of intermolecular forces affect the magnitudes of these physical properties that we've discussed. Can we make any conclusions? Write them down if you can make any see any trends or make any conclusions. Write them down. We're going to come right back to this, and it's good for you to know what you were thinking at this point. So just as we examined factors that affected the strength of hydrogen bonding interactions, I want to take a moment and think about factors affecting London dispersion forces. In this table from your textbook, we have the melting point and boiling point data for several nonpolar molecules. Pause and write down any trends that you see in this data. We will examine a few sets of molecules. Let's begin with chlorine, bromine, and iodine. Think about the relationship of these three molecules to one another, and then take a look at the melting points and boiling points of these three substances. What trends do you see? These are all halogens located in group 7A. We know that atomic radius, and then hence the size of the molecule, increases down a column. The data on the previous slide pretty well suggested that stronger intermolecular forces of attraction, such as hydrogen bonding, led to higher melting points and boiling point. From this data, we can conclude that as the size of the molecule increases, so does the strength of the intermolecular force of attraction between these molecules. In other words, two iodine molecules having bigger electron clouds than two chlorine molecules will experience stronger London dispersion forces, stronger induced dipoles. Along with those stronger intermolecular forces of attraction come higher boiling points and melting points. The next set of molecules we can look at would be methane, ethane, propane, butane. Let's zoom in on these molecules. And I would say it might be the most straightforward for us to look at boiling points here. What conclusions can we make from this data? We can note the pattern first, that as the number of carbons increases, so does the melting points and boiling points. Particularly here we see the boiling points of these compounds. So we see that pattern. We will conclude that the intermolecular forces increase with more carbon atoms in the chain. We suspect that this is related to larger electron clouds for butane with 4 carbon atoms compared to methane with 1 carbon atom. More electron cloud, more places for these induced dipole interactions to occur, and overall stronger intermolecular forces. The last set of molecules you'll look at, dimethylpropane and pentane. Both of these molecules have molecular formulas of C5H12. So they have the same number of electrons, they have the same molar mass. They have very different melting points and boiling points. How can we rationalize this data? We can conclude that there are stronger intermolecular forces of attraction between molecules of pentane since it has a higher boiling point than dimethylpropane. This is because the electron cloud of a straight chain alkane, like pentane, has more surface area and thus more places to make these induced dipole-dipole interactions. So overall, there are stronger intermolecular forces of attraction between these straight chain alkanes, lots of places to make induced dipoles, versus these branched alkanes where there's less surface area, so dimethylpropane, and fewer opportunities for these induced dipole interactions to form. Wonderful. Now that we know the factors that affect the strength of London dispersion forces, let's make sure that we are crystal clear on what trends there are in intermolecular force strength and how these trends are related to physical properties. I would like to point something out. I'm using the word trends, patterns, right? These are patterns, and there are certainly exceptions. There are several exceptions on this slide here, and I'm sure you're wondering what they have to do with, and I welcome you to send me a message and ask me about any exceptions or anything confusing that you see in any of this data. When we refer to trends, though, these are just patterns, and there will be exceptions. Often we can explain them, and sometimes we can't, and that's okay, but we need to look for the patterns. Take a moment, summarize the past couple of minutes, make sure that you can answer these questions. In general, the strongest type of intermolecular force of attraction between two molecules is the hydrogen bond. Of course, we know that multiple hydrogen bonding interactions affect the strength of this intermolecular force for a given molecule, and then also the polarity of the XH bond. Second, the dipole-dipole is a little less strong than hydrogen bonding interactions generally, but it's stronger than London dispersion forces, which operate for all molecules, but are most significant for nonpolar molecules. It was demonstrated by the data on the previous slide that the size of electron clouds really affect the strength of London dispersion forces. Generally, the larger the electron cloud, as indicated by each of these three sets of molecules that we discussed, the stronger the London dispersion forces are. You may notice we've been glossing over or haven't mentioned the ion-ion forces, such as in the conjugate base of methanoic acid. So if we treated methanoic acid with sodium hydroxide is a base and would deprotonate this acidic proton on methanoic acid. And then the opposites would attract here. So we have this ion-ion interaction within this compound. And certainly for this substance, there's the highest of all boiling point, the highest melting point. So why is that? Why are ion-ion forces even stronger than hydrogen bonding interactions? Well, yeah, it's because you have full charges. The greater the magnitude of the charges, the stronger the attraction between them. How are these trends related to physical properties? Well, in general, the stronger the intermolecular forces of attraction are between two molecules of a substance, the higher the melting point, the higher the boiling point, the lower the vapor pressure, and what others? Okay, I'm sure you can list them. So list them. And once you've done that, we're going to move on and think about, well, why are all these phase-related properties so tied to the intermolecular forces of attraction between two molecules? All right, so stay tuned for that. Before we do that, we're going to just practice for a quick moment. Consider which pair of species will have the strongest intermolecular forces of attraction and which pair of species will have the weakest intermolecular forces of attraction. Pause. The strength of the intermolecular forces of attraction here are related to the type. So start by identifying the type of intermolecular force of attraction between each substance. So for A, you have ion-ion forces. For B, these are polar molecules, and we will have dipole-dipole forces of attraction because there are no FH, OH, or NH bonds. C, however, does have NH bonds, so we will have hydrogen bonding interactions between molecules of this substance. Now, which is the strongest intermolecular force of attraction of these? Yes, ion-ion, then hydrogen bonding, and then dipole-dipole be the weakest of these three. Related to this question, which of these substances do you expect to have the highest melting points and boiling points? Yes, those will correspond to the substance with the strongest intermolecular forces of attraction. I've taken our answers from the previous slide and pasted them here. Since substance A has ion-ion forces, which are the strongest intermolecular force of attraction, we do expect substance A to have the highest melting points and boiling points. Substance B, we expect to have the lowest melting points and boiling points. Now, as promised, let's talk about how and why phase change relates to the strength of intermolecular forces of attraction between the molecules of a substance. Recall the microscopic differences between the phases of matter. The solid has the smallest particle spacing, liquid has medium particle spacing, and gas phase has the largest particle spacing, the largest distance between two molecules of a substance. This results in the solid having the strongest intermolecular forces of attraction, and the gas phase having the weakest intermolecular forces of attraction for the phases of a given substance. Recall, intermolecular forces of attraction are simply electrostatic attractions. And if we think about electrostatic attractions, they're equal to a constant K times the charges of the charged bodies divided by the distance between them squared. So the larger this distance gets, the weaker the attraction between the two particles. Thus, distance between the particles is so large in the gas phase that the attraction between them approaches zero. So we can ignore them. So when a substance transitions from the solid to the liquid and the particle spacing increases, that disrupts the intermolecular forces of attraction, and heat must be added to disrupt those intermolecular forces, to move those particles apart. Imagine they're magnets attracting one another. Likewise, when a liquid transitions to a gas, once again, intermolecular forces of attraction must be disrupted. This time, they must really be removed all the way because in the gas phase, intermolecular forces are negligible. The molecules are too far apart to experience attraction. So again, heat is required to disrupt those intermolecular forces. And then the heat required, the amount of heat required, is related to the boiling point of that substance. Just like the amount of heat required for the solid to liquid transition is related to the melting point of the substance. I've summarized on this slide why intermolecular forces of attraction affect the melting point of a substance. So you have a nice typed writing. We will now revisit this question from the very beginning of class. We looked at estradiol and cholesterol, and we wanted to explain in as sophisticated of a manner as possible why estradiol has a higher melting point than cholesterol. Write down your best explanation to this question now. Because estradiol has two polar OH functional groups compared to the one on cholesterol, it makes more hydrogen bonding interactions than cholesterol, so overall has stronger intermolecular forces than cholesterol, and as a consequence, a higher melting point. How can we explain the difference in solubility between these two compounds? Well, I think we did a pretty good job of explaining that at the beginning of the lesson. Solubility is more related to two substances having similar intermolecular forces of attraction. Because we're talking about solubility in water, which is a polar molecule, the more polar of the substances will be more soluble in polar water. You may recall what factors determine whether or not two substances will mix. Write them down. Most students remember the rule likes dissolves likes. And although likes dissolve likes is an easy rule to remember, we should recall that solubility is driven by the same energetic considerations that drive all processes of the universe. In other words, think about delta G. The entropy of mixing is always favorable. The enthalpy of mixing, however, may or may not be favorable. In order for the enthalpy of mixing to be favorable or negative, the intermolecular forces that the two substances you're mixing, let's imagine you're mixing substance A and B, and you want to know, are they going to mix, make a homogeneous solution, or are they going to not mix, make a heterogeneous solution? This really depends on whether or not A and B can make intermolecular forces with each other. And in order to make an intermolecular force of attraction with each other, they need to make the same type of intermolecular force of attraction. And because the types of IMF that a substance makes determines its polarity, then this rule, likes dissolves likes, makes sense and works out, and you can just remember it. But at this point, as we're becoming more and more sophisticated, we need to understand why. Polar substances dissolve other polar substances, and nonpolar substances dissolve other nonpolar substances because each of those pairs will make the same type of intermolecular forces of attraction. We'll look at a few examples of this. So we can explain why hexane and water are insoluble, so they do not mix, while ethanol dissolves in water in all proportions. In other words, they do mix. So if we were to take some hexane, which has a structure like this, and mix it with some water, as the diagram shows, those substances would not mix. In fact, a heterogeneous substance would form, where hexanes would be on top of water because it is less dense than water. We can understand this now, as hexanes is nonpolar and makes London dispersion forces, whereas water is polar with an OH bond, and so it makes hydrogen bonding interactions. These are not the same. So these two substances, water and hexane, they can't interact. They can't attract one another. They can't make a significant attraction with one another. And so the delta H of mixing is positive. It's unfavorable. And so they don't mix. On the other hand, ethanol and water both make hydrogen bonding interactions. And so because they both make hydrogen bonding interactions, they can engage in intermolecular forces with each other. Look at all those IMFs we have shown here. And because they can make intermolecular forces of attraction with one another, they do mix. And they do it so well that they mix in all proportions. I hope that sounds somewhat familiar. Let's continue talking about this and look at another example. Explain why sucrose is soluble in water based on its molecular structure. Pause and write down your best answer to this question. Okay, if you're back, also pause and identify functional groups. Sucrose is a disaccharide. It is made of a glucose and a fructose. So we can see that because this is a carbohydrate, it has many alcohol functional groups. And then it has the two acetals, which are derived from the aldehyde group of the carbohydrate in its acyclic form. But in sucrose, the carbohydrates are in their cyclic form. And what is important here is that sucrose has many polar OH bonds with which it can hydrogen bond to water. And because of that, it dissolves in water. It has quite a high solubility in water, in fact. Excellent. All right, we can do this. Let's look at our functional group charts. Which of these functional groups do you think will result in water solubility? And is there anything else that you should consider when you are evaluating the solubility of a molecule? Okay, this is not going to be an exhaustive list, but you do know that water hydrogen bonds. You know from general chemistry that water can dissolve salts and polar molecules, typically small polar molecules. So if we think about the functional groups that will be able to make or accept hydrogen bonds, certainly there's the carboxylic acid, there's the alcohol, and there will be others. Certainly some other carbonyl-containing functional groups like aldehydes and ketones may dissolve in water. And what about these other things you should consider? Well, you need to consider the R group. Okay, so if we have an aldehyde or a ketone, we need to consider these R groups. Organic molecules are complicated. There are lots of atoms. So you need to think about how large or how nonpolar is the R group because it can counteract the polarity of the polar functional group, the carboxylic acid, the alcohol, the carbonyl of an aldehyde or ketone. We saw that in cholesterol and estradiol, right? Estradiol has two alcohols, but because it has this huge nonpolar part, it really doesn't dissolve very much in water. And then cholesterol is even worse. It has an even bigger nonpolar part, and it's virtually insoluble. I mean, honestly, they both are, but even less soluble cholesterol than estradiol. So there's some subtlety, and we just have to, take a look, take a deep breath, and learn, how large is too large. So for example, with alcohols, when are there too many carbons so that alcohol doesn't dissolve in water anymore? That's something that you need to explore in the lab that we'll do. I will hit a few more points and then we'll be done. What do you think is an ion dipole force? And when do you think it is significant? Yeah, so on the previous slide, I mentioned that water dissolves salts and polar molecules. And well, how does water dissolve salts? So the partial positive end of water is electrostatically attracted to anions. The partially negative end of water is electrostatically attracted to, yes, cations. Where do you think these forces fit into our list in terms of strength? The strength depends on the size of the charges. So we certainly have bigger charges here than we do with hydrogen bonding, but not quite as big as with ion-ion because water just has partial charges. So yeah, ion dipole forces, they're going to fit right in here. We'll consider an example of this now. Let's explain why sodium chloride dissolves in water, but not in DMSO, which stands for dimethyl sulfoxide and is a common organic solvent that you will encounter both in biology labs and chemistry labs. So stop, write down your answer, and maybe it helps to know the structure of DMSO. Usually it's drawn like this. Don't worry about the Lewis structure, just this is it. So go ahead and consider this question. Well, I'm getting tired, so I'm going to cheat and use the picture from the book. Well, water is a polar protic solvent. So what that means is that it has a polar OH bond. And so this is a big partial plus here on hydrogen due to that polar OH bond. And because of that, it strongly attracts anions, like we see here with chloride. So this big partial positive strongly attracts anions. DMSO, on the other hand, is aprotic. It does not have a polar OH bond or polar XH bond. Because instead of having the partial positive on hydrogen, little hydrogen, so pretty dense partial positive here, also very polar bond, so big partial charge in a really small area. Instead of that, DMSO actually has the positive charge spread out. So it's just spread out over here, so more diffuse positive charge. Now, sorry, I draw this molecule like an inorganic chemist. Don't worry about the fact that I'm drawing a single bond and this is a double bond. Let's not worry about it. But just stay with me. This is a diffuse partial positive here. It's spread out on all these atoms. And because of this, you're going to have a weaker attraction to anions. So we can draw it, but there's a much weaker attraction to anions here. And because of that, sodium chloride does not dissolve in DMSO. DMSO cannot stabilize both ions like water can. DMSO does fine with the cation. That oxygen has a significant partial negative sticking out there, accessible to the sodium ion. So it's okay for the cation. It just doesn't solvate the anion very well because of that diffuse positive charge. You should be able to distinguish between protic and aprotic solvents. Again, protic solvents have the polar XH bond. Aprotic solvents do not. They're still polar, right? There's still a polar bond here. They just do not have the superpolar OH bond. And of course, the consequence of that is the type of intermolecular forces that these molecules make with themselves as well. Be sure that you can summarize each of these types of intermolecular forces and how they affect the physical properties of molecules. You can identify the predominant intermolecular force of attraction for a given molecule or even a functional group based on its polarity. And then, of course, we have to check for a polar XH bond, where X equals fluorine, oxygen, or nitrogen. You can identify hydrogen bond donors and acceptors. The donor is that polar XH bond, and then the acceptor is a lone pair, which either from a different molecule, or if we're thinking about just molecules of XH, then it's a lone pair on X. You can explain how the physical properties of a molecule relates to its intermolecular forces. And finally, you can identify protic and aprotic polar solvents. So they're going to be polar, but the protic ones have this polar XH bond, and the aprotic ones have no polar XH bond. Take a moment, summarize what you learned in this lesson. What was review and what was new? And then finally, think of what questions you have and ask me. Time to practice.